Well, today we'll have a shorter topic, and so I'll actually start a second topic. First topic we want to look at is the sum to product. And product to sum formulas. These are the last identities we're going to do. The rest of them, the idea is that you can figure them out if you need them from the identities you memorize. And what I would like you to do is memorize all those identities we had to date, right? The Pythagorean identities, the cofunction identities, etc. The sum and difference, the double angle and half angle identities. These are used less, but they're used occasionally. What I say with these is don't memorize these, but be aware they're present in case you need them sometime. So don't memorize. You're welcome to if you want. It certainly doesn't hurt. Use them a lot, but the point is that these are not used very often. So I won't require you to know these on the test. I'll give them to you on the test if you need them. And here's the derivation. I almost think the derivation is easier than memorizing them. We'll say the first derivation comes from our cosine alpha minus beta. Cosine plus sine. Remember with cosine, the difference formula minus goes with plus. And then we have a very similar looking sum formula. Cosine of alpha plus beta is cosine minus sine. And you realize that if you were to just take this first one and add it to the second one, take this one on top plus the one on the bottom, I get an interesting identity also. So if I take this one plus this one, I've got cosine alpha plus beta plus cosine alpha minus beta, adding the two left-hand sides, must be equal to this one plus this one. Well, there's two of those, two of the same thing. So it's 2 cosine alpha cosine beta. And then you add these and you get nothing. Now take this and switch sides and divide by 2. So this on the right comes over on the left and is divided by 2. And what you get is just cosine alpha cosine beta. This one over here and divided by 2. Take this one over here and divide it by 2, and you've got 1/2 cosine alpha plus beta plus cosine alpha minus beta. All right. That is a product converted to a sum of cosines. This is one of the amazing things I found about trigonometry. If you multiply two waves, you can rewrite it as 1/2 the sum of two waves. That's kind of strange, isn't it? But it's actually a very important concept in engineering, where they might have a circuit that's got an alternating current running through it, and you've got two of these waves multiplied, and you come out with sum of two waves. But it really makes for some interesting results sometimes, one of which I'll show you today. I got a video for. So we'll call that equation 1. This is a product to a sum formula. Now, similarly, suppose we instead subtract above there. But you can see why I say it's easier to memorize the proof sometimes than the formula. This formula isn't too bad to memorize. I find this to be the easier of the ones that we're going to do, although they're pretty similar. But if I remember these two, and I do, I use these a lot. I just think in my mind of adding these on the left and the signs canceling out. And I get this with a factor of 2 just by kind of thinking of it in my head. Suppose I subtract these. Now I've got this one minus this one. Cosine alpha minus beta. Subtract cosine alpha plus beta. Yes, this one minus this one. Now the cosines cancel and you get 2 of these. This one minus a minus is plus. twice sine alpha sine beta. And now you can see where I'm going with this. If I just divide this by 2 and switch sides, then on the left, I've got sine alpha sine beta. Right, I've got half of this one. Half cosine alpha minus beta less cosine alpha plus beta. That one will be formula number 2, another product to sum, right? Sine times sine can be written actually as a difference, but we still call it a product to sum formula. You can think of it as plus minus this one, plus the negative of that one. There's cosine converted to a sum, sine converted to a sum or difference. Finally, well, if the cosine sum and difference formulas can get you some of these product to sum formulas, maybe we can get one also from the sine sum and difference formula. We use the sine alpha plus beta. Looks like sine cosine plus cosine sine. And the sine difference formula looks like sine alpha minus beta equals sine cosine minus cosine sine. And suppose I add these. On the left, I've got sine alpha plus beta plus sine alpha minus beta. And on the right, these two cancel, they're the same, and these two add to get 2 sine alpha cosine beta. Now, if I divide by 2 and switch sides again, I get the last product to sum formula. But the same kind of proof every time. So if you just remember that, then you can do all 3 of these. You don't have to remember any formulas, right? Anyway, so that's the idea. Now I've got over here sine alpha cosine beta. 1/2 of the right side equals 1/2 of the left side is 1/2 sine alpha plus beta plus sine alpha minus beta. We can call that formula 3. And now we can write a sine times a sine, a cosine times a cosine, or a sine times a cosine as a sum of sine functions or cosine functions. Any questions on those? The homework is very simple on this, and it's so simplistic you don't see the use for it. Well, let's just try one homework problem on this. I'm going to assign very little homework. There's only 3 in the list here if you look. Let's try this one. Example, this is 1B out of the homework that's coming up. Convert this product to a sum. 20 cosine 36t cosine 6t. Convert to a sum. And the idea on a lot of these is just to recognize this looks like something you've seen before. When you see cosine times cosine, you think, wait a minute, a product can be converted to a sum. What I have to do is just remember that cosine times cosine by equation number 1 is 1/2 of something. So this is 20 here times 1/2. If I call this alpha, this beta in the formula, see cosine alpha cosine beta is 1/2 cosine alpha plus beta, so I'll put cosine plus beta plus cosine alpha minus beta. And then alpha is 36t, beta is 6t. And this simplifies, right? 20 times 1/2 is 10, and that multiplies cosine of 42t when I add those together, plus cosine 30t. When I subtract those. There we go. Or you can call it 10 cosine 42t plus 10 cosine 30t. I'm just looking for that if I say convert to a sum. Okay. That's all it does. It allows you to rewrite these things. Why would that be useful is not real obvious here. Sometimes in applications, maybe you're interested in graphing something like this. Like suppose I wanted to graph this thing, 20 cosine 36t cosine 6t. I could have an idea in my head what it looks like. Not from this. How do I multiply two waves and right, each one I know what it looks like, but what's their product look like? I might figure it out easier from the sum, right? So note, this is not in the homework, but graphically, we can kind of imagine in our head the result we get. Suppose we were to plot 10 cosine 42t. Well, we know cosine starts at its maximum amplitude, so it starts at 10. And it goes down to minus 10. Right? And so cosine 42t, what does this have a period? From the 42t, period of this thing ought to be 2 pi over b, right? This is a cosine bt, and c and d are 0, so there's no shift. 2 pi over 42, pi over 21. So this completes a period at pi over 21, we can figure. And it looks like that. It goes between plus and minus 10. And how about this one, 10 cosine 30t? Well, this is a cosine bt. It has b equals 30. And so the period here, period 2, if you like, is 2 pi over 30, pi over 15. And I could sketch that one a little longer, right? Pi over 15 is bigger than pi over 21, so it looks about like this, maybe. Now I can sort of tell what their sum looks like. It's not real obvious, but the sum I can get by stacking these. When they're both at 10, you add the two of them together and you get up to 20, right? So initially their sum is there. Now when you get down to this point, you're adding 0 from this one to this one, so you're lying right on this function. Here you're adding 0 from the blue one to this one and the black one, so you're about there. And so the function, the sum of them looks something like that. And then down here, this one's minus 1, and this one's kind of close to minus 1. If I just take it and stack it down here, it's something like that. And maybe they reach a minimum somewhere in here. And when this one's back to 0, we add it to this one and get back to here. So we're going back like that. And let's see, over here, we take this one and stack it on top of that one. Maybe we're there. And so you get the rough idea what this looks like. This black one will then keep coming down here. Over here, maybe we take this one and stack it on top. Oops, it's not coming down quick enough, is it? Something like that. So let's say this should probably go a little higher than that. So this one, right? What? Right here, when this one is 0, we should be on this one. I didn't draw that very well. That. It comes up through here, but you can get a rough idea in your head what it looks like by thinking of what does the sum of those two y values look like. There's one advantage of being able to rewrite a product as a sum. Amazingly, though, there's a second thing you do. Sometimes you might want to write a sum as a product, right? That's the other kind of formula. So we'll say don't memorize these three, but be aware they're available. You can rewrite a product as a sum. Similarly, we can do the following trick. We ought to be able to convert a sum back to a product, right? Here's how you do it. You just let x be alpha plus beta and y be alpha minus beta. You can rewrite the sum back in terms of x and y over here. Now substitute. I'll let alpha plus beta equal x. Actually, let's do alpha minus beta equals x. and alpha plus beta be y. And 1 becomes, well, if we're going to substitute, really, we need to replace alpha and beta independently here too on this side. So let's see if we also have, let's see, x equals alpha minus beta, y equals alpha plus beta. You add these, you get x plus y equals 2 alpha, right? Because the betas cancel. And if you subtract them, you've got y minus x equals 2 beta. So evidently alpha equals x plus y over 2. And beta equals y minus x over 2. And now 1 becomes cosine alpha, which is x plus y over 2. Cosine beta, which is y minus x over 2, equals 1/2. Cosine alpha plus beta is y plus cosine alpha minus beta is cosine x. So that's what equation 1 comes by making the substitution. X is alpha minus beta and y is alpha plus beta. Equation 1 into this. And now you multiply it by 2 and switch sides. On the left, this comes over and I get cosine x plus cosine y. Right, just twice this one on the left, and then twice this one on the right is 2 cosine x plus y over 2 cosine y minus x over 2. Boy, wouldn't that be nice if it was x minus y instead of y minus x? That'd be easier. It is actually, if you want, right? Because y minus x over 2 you can also write as minus x minus y over 2, right? Plus y minus x all over 2. And then cosine of a minus an angle, same as cosine of a plus. It's an even function. So we can just switch it and write x minus y over 2. So cosine x minus y over 2 is the same as cosine x y minus x over 2. And we have this identity here, which I can call 4. This one is a sum to product identity. So you just take this product to sum identity, place alpha plus beta with y and alpha minus beta with x, and you got this sum to product identity. Now I can rewrite the sum as a product. And you can do that with each of the other two also. So this one converts into this one just by a substitution. All right, so cosine plus cosine converts. And then similarly 2 by the same substitution. Two becomes what? Let's see, sine alpha, sine beta. Here's alpha and beta becomes sine, let's see. Alpha is x plus y over 2. Beta was y minus x over 2 equals 1/2 times cosine alpha minus beta x alpha plus beta becomes y. Then I'll take minus 2 times each side. Switch. So multiply by -2, switch sides. What you get out of this is cosine y, actually, let's just multiply by 2. Let's say cosine x minus and switch sides. Cosine x minus cosine y, this one, multiplied by 2 becomes this one multiplied by 2. Twice sine x plus y over 2 and sine y minus x over 2. We call that equation 5. Now, if you have a difference of cosines, you can rewrite sum of cosines to a product, difference of cosines to a product, and you do the same with the sines also. Line number 5 here. Also substituting 5. When we do these proofs, actually, because these things are so hard to remember, that sometimes it's easier to remember just to make these substitutions and convert them over. Substitute in 5 by the same. And you've got, let's see, alpha is x plus y over 2, so it's become sine x plus y over 2. Cosine beta is cosine y minus x over 2 becomes 1/2 sine, and then alpha plus beta was y. Alpha minus beta was x, so sine y plus sine x. And equivalently, by multiply by 2 and switch again sides, we get finally sine x plus sine y, twice the left side, equals twice the right side. Twice sine x plus y over 2 cosine y minus x over 2 is also x minus y over 2 by the even property. There we've got equation 6. Sum of two sines can be rewritten as a product of a sine times a cosine. And you can make one more of those if you put sine minus sine. We should write that down just to be complete here. Put y equals minus y in this one. Minus y for y here. So sine of minus y becomes minus sine y. This left side becomes sine x minus sine y. Sine is odd, so when you put minus y, it comes out and writes minus the sine of y. Becomes 2 sine x minus y over 2, replacing y with minus y. And here, this one becomes cosine x plus y over 2. Replace y with minus y. That's 7. So there's 7 of these that are worth being aware of. But if you have a sum or difference of sines or cosines, you can rewrite them as a product of sines and cosines. That's the point. Just remember you can do that and you can look up these formulas. Any comments or questions on those? Those are the derivations. Figure them out sometimes if you need them. Let's do an example from the homework again. Again, it's very simple. I just give you a sum test also and ask you to convert it to a product. Sum or difference and convert it. So here's number 2, A. Convert this pair, cosine 6t plus cosine 4t, to a product of sines and cosines. Suppose you added these two ways. How do I go back the other direction? I'll say by formula 4, that's supposed to be equal to 2 times cosine of the sum over 2, cosine. If I call this x, and this y in the formula, it's supposed to be x plus y over 2. times cosine x minus y over 2. So you just call this x and call this y. Now I've got 6t plus 4t all over 2 here, and 6t minus 4t all over 2 here. So I'll convert this one with x equals 16, y equals 4t. But now 6t plus 4t over 2 is just 5t. It's the average of these two, 6t and 4t. This one is the difference over 2. So we get 2t over 2 is cosine is t. There it is. That's all you have to do for now. I might ask you something like that on the test. Then the question is, what good is this one? This is kind of an interesting answer, actually. Suppose I have something that makes a nice, clear sine wave for sound, for instance, like a tuning fork, right? People strike this metal object that looks kind of like this. It's called a tuning fork. And it makes a rather clear note. It makes us almost sinusoidal vibrations in the air, right? What you're hearing in the air is you're hearing changes in the pressure of the air. As you strike this thing, the tines here wiggle back and forth and cause a difference in pressure from the ambient pressure of the room. And so the pressure jiggles a little, and your ears are sensitive enough to pick that up. Ears are incredibly sensitive machines, if you like. And these tuning forks, they like to use in these experiments because they make almost sinusoidal waves. Unlike your voice, when you make your voice, and your voice makes a big jumble of waves that kind of have pulses like this, and the length of each pulse determines the note approximately. So you get pitch. You have a certain pitch, you know, because it sounds like you're making a certain note, but actually the wave is a jumble that just kind of comes across that way. And then what kind of jumbles you like, tell you what kind of people's voices you like. But these make a very regular, nice sine wave because they just wiggle back and forth, and that's all they do. So you can do a more clean argument with these. This might make a sine wave with maybe it's a C note or something. And then you take a little different size tuning fork, maybe like that, the metal thing, again, you strike it and it produces pressure variation in the room, and maybe this one makes an A note. What happens if you strike these two things at the same time with the same amplitude, so they're the same loudness, if you like? Then what you do is you get a pressure variation in the room, which is, suppose the amplitude is 1, you can get a cosine of BT from this one, and you can get a cosine of B1T and B2T from this one. A little different value of B, we call B the angular frequency. And if they both have the same amplitude, like they're both 10 or something, then you can combine these using this formula, right? Because it's just like this, cosine plus cosine. And what they do is they combine into a single cosine. And so this one would be 10 cosine, their average, B1 plus B2 over 2, T times cosine B1 minus B2 over T, or 2T. And so it'll look like a product of cosines, and the graph comes out very interesting. For instance, on this one here, how do I figure out how to graph this when it's a product? Well, like I said, in the general, it's kind of hard to tell what the product is. But when these two frequencies, these two B's here, were pretty close together, like 4 and 6, then when you add them over 2 and divide by 2, they give you very different numbers here. And so these actually have much different periods. If I plot, just forget the cosine 5t, 2 cosine t, I know it looks like this. And it has period 2 pi. T versus y, maybe this is y equals. And it goes between plus and minus 2. That's just this one, 2 cosine t. Now, what is if I multiply that by cosine 5t, this oscillates between plus and minus 1 much faster, right? Because its period is only 2 pi over 5, right? And so this is period 2 pi over 5. This one is period 2 pi. And so what you're doing is taking this one, which is y equals 2 cosine t, and you can draw this other picture. Here's minus that function. It equals minus 2 cosine t. And if this oscillates up and down real fast between plus and minus 1, and it does, and what you do is the product of these is kind of like this. And what you have then from this, you can draw this a little further out here too, is a product wave that oscillates up and down in beats between plus and minus the 1 function, 2 cosine t, just real fast because it's multiplied by this thing that goes real fast between plus and minus 1. And so each of these pulses here is called a beat. And within that, there's a natural frequency that you hear. And so when your ear hears this, instead of hearing a C note and an A note both, what you instead hear is a frequency that's halfway in between the two of them, right? That's the cosine 5t, halfway between maybe the A note and the C note. These aren't actually frequencies for A and C that I wrote here. It's just an example. And then it goes on and off, and you can hear this beats, the sound going on and off. Both tuning forks are playing a constant loudness, and yet what you hear is the sound going on and off with a frequency that's halfway in between the two notes that you played. So I'll illustrate it with a short video here. This is an MIT video that does one more thing first. It first illustrates that. Let me put the picture up. I apologize online, you won't be able to see this, but you can go to the website. Just if you Google MIT phenomenon of beats, you can get this video to come up and watch it yourself. Maybe I'll send out the link if I remember to. But it doesn't carry online for some reason. Let's see if I can play this now, just a little bit. Here's two tuning forks. This is a tuning fork with its handle stuck down in the box. This is another one, handle stuck down in the box. So the box are going to amplify the sound, make it louder. And what you can do is strike one of these tuning forks. Right now, they're identical tuning forks, so they play the same frequency, both a C note or something. I don't know what note they're actually playing. You can, maybe somebody's a piano major or something can tell me. But if you strike this one and you put the two boxes together, then the echo from this one goes into the other box and makes the other one jiggle at the same frequency, right? Because its natural frequency is the same, a C note. So you can translate the C note from this one to this one. And here in the second box, that's the first demonstration he does. Then, if you put a clamp on this one, it changes the frequency. It won't vibrate at the same frequency as it did before. And so now when you strike this one and put the boxes together, it won't translate the vibration from this tuning fork to this one, because this one has a different natural frequency. It wants to, when you strike it, wiggle at a different rate. And so you can't use the sound from this one to produce the sound on this one. That illustrates the ideas of antennas. Antennas do the same thing. They send out radio waves, right, from one antenna to another. And the second antenna only picks up the radio waves from the first one if it's got the right length to absorb that same radio wave. It's like the sound transmits through pressure. The radio waves transmit through electromagnetic radiation, we call it. And so the same thing happens on your radio. You only get one station because it depends on what frequency you set out, if it's the same as the transmitting tower's frequency. And so that's the first illustration. It's for antennas. You can transmit the same to an antenna with the same frequency, but not to an antenna that absorbs a different frequency. Then the last demonstration, what he's going to do is leave the clamp on here, and so you have slightly different frequencies, like an A note and a C note or something. And he'll strike this one and this one separately. And when they're both playing with the same loudness, roughly, what you hear is not sound of both of them at once, even though they're both making a pressure variations in the air, but you hear a sound that goes on and off, and the note is halfway between, like we just did there with the with the sum to product identity. So this is how, where the sum to product identity shows the result you get physically. Sum to product formula. All right. I need that nice clean board over there. This is all of that. So those aren't used as much, but you do want to be aware of their presence so you can do things like the phenomenon of beats. The rest of the period here, I want to talk about solving trig equations. We'll get a new topic. How about that? This comes up to be very important in lots of science classes. You have to do these kinds of things. And what we're going to do is start with very simple ones and then gradually make them harder and harder and harder. And the first one then will just be to solve a trig equation that consists of a trig function equal to a number. Suppose that's my problem. How can I solve that? You might guess right off, probably the unit circle, right? Sure enough, what you can do is this, is let theta be the angle, whatever it is, 2x or 3x, whatever you're taking the trig function of. And then solve for theta in the unit circle. All possible theta on the unit circle. Better move this. Once you have that, theta is some function of x, and then restrict x as is given in the problem. Apply any restrictions on the original variable x. Have to from all possible values. This really needs an example to illustrate it. For instance, suppose I want to solve the equation sine of 2x equals 1/2, but I don't want to just take any x. I just want x within one rotation. So I want 0 less than or equal to x less than 2 pi. That's the restriction, right? how do I find all possible x within one rotation, because I'm only interested in the direction x points, that satisfies sine 2x equal a half, right? Trig function equal a number. Well, I can appeal to the unit circle according to this by writing theta equal 2x. I write this now as sine theta equals a half. That's a little easier, right? And I'll put that on the unit circle. Sine is the y coordinate. So if I draw the horizontal line, y equals a half, all points with y equals a half. And sine of theta equals a half is a point whose y coordinate on the unit circle is a half. And these are the only points in the unit circle that are possible to get sine theta equal a half. So there's only two possible terminal rays, right? Like y equal a half here or y equal a half here. So only two possible terminal rays, and now I can figure out what angles theta can give me those values of y. Well, if I drop a perpendicular here, this went from y equals 0 to y equals a half, this side length is a half. This is 1 because it's a unit circle. That forces this side, right, by the Pythagorean theorem, and we already memorized this triangle. It must be square root 3 over 2. We could figure that from the Pythagorean theorem, but we know it. Let's write it down. So there's this triangle here, and then by symmetry, this one is always the same. Remember the 1/2 square root 3 over 2, one triangle has an angle here, pi over 6 in radians, 30 degrees. So this one must also be pi over 6. And we observe there's exactly two angles within one rotation for theta that can give those two terminal rays. Theta equals pi over 6 evidently. Or theta equals this one, right? Which is pi back up pi over 6, 5 pi over 6. 6 pi over 6 back up pi over 6 makes 5 pi over 6. So those are the two angles theta within one rotation. But now what are all possible angles theta? So I'll say find all possible theta. What are they? What are the other angles? There's an infinite number of solutions actually. Do you see it? What we showed is there's only two terminal rays, but that means all coterminal angles will have the same values of the trig functions, right? So all angles that have those terminal rays are this plus any multiple of 2 pi. We can write k times 2 pi, where k is any integer. It could be 1 or 2 or 3 or 4. It could be -1, -2, -3, -4, or 0, right? So any plus or minus any whole number, any integer we call those, right? A number with nothing after the decimal point. So any plus or minus any whole rotations, k 2 pi. And then we don't like to write k times 2 pi. We like to put the 2 first. So instead of, for k rotations, instead we'll put 2k pi. So here's pi over 6 plus k rotations. And 5 pi over 6, you can add any plus or minus any whole rotations and put 2. Any integer number of rotations. There are all solutions theta. This angle, pi over 6 plus k rotations. This angle, 5 pi over 6 plus any k rotations, is an integer. And when you just put k, everybody assumes, unless you say otherwise, that it's an integer. Here are the integers: 0 plus or minus 1 plus or minus 2. You don't have to write that. If you write k instead of x, I'll assume it's an integer unless you say otherwise. So those are all possible values of theta to get sine theta equals a half. Now, how do I solve the original problem, sine 2x equals a half? Let's put back x, 2x equals theta, right? That was the original substitution. So now I'll say, but theta equals 2x. And then I can divide both sides by 2, right? And say equivalently, all possible x, dividing by 2, are x on the left there equals pi by 2 on this side, pi over 12. And divide 2k pi by 2, and I just get k pi. Right? So I divide the whole left by 2 and the whole right by 2. Similar in the second one, divide this by 2, I get x on the left and 5 pi over 12 plus k pi on the right. And I'll leave out the k equals in the statement. Assume that. So there's all possible x. If I ask you for all solutions to this problem, that's the answer. There's an infinite number of them, one for each k. However, I didn't do that here. I made it harder. I said, suppose x has to be between 0 and 2 pi. Now, what are the allowed values of x? So here's all x between 0 and 2 pi within one rotation. What are those? All you do is you take all values of k that give you an answer between 0 and 2 pi. So I try k equals 0. You try small numbers and see what you get. If I put k equals 0, I just get pi over 12 plus 0, so I get pi over 12, right? For the first one. Then I put k equals 1, and I'll say, oh, then I get pi over 12 plus 1 pi. Which to add these, I need a common denominator, so I'll write that as pi over 12 plus 12 pi over 12. Oh, pi and 12 pi is 13 pi. 12, that's between 0 and 2 pi, right? 2 pi would be 24 pi over 12. So 13 pi over 12 is a solution that I get by putting k equals 1 in the first equation. And then that's it from the first equation. Can you see that's it? You just try at least small values of k until you get it too big. Putting k equals 2, now you've got 2 pi plus something positive. It's too big. It's bigger than 2 pi, right? So I don't even need to add it. I just know that 2 pi plus a positive angle is too big. If I put in minus pi plus a 12th pi is going to be negative, right? This is a whole pi subtracted and only pi over 12 added. That'll be negative. So k equals minus 1 doesn't work. Only k equals 0 and k equals 1 in this first equation give me angles between 0 and 2 pi. How about I haven't tried the second equation, right? So I'll try k equals 0 in the second equation. I get 5 pi over 12. That's between 0 and 2 pi, right? Between 0 pi and 24 pi over 12. And I'll try k equals 1. And in k equals 1, I've got 5 pi over 12 plus 1 pi. So there's k equals 1 in the second equation. It gives me 5 pi over 12. 12 pi over 12. Must be 12, 5 and 12 is 17 pi over 12. That's between 0 and 2 pi. 2 pi would be 24 pi over 12. So I've got 17 pi over 12 as a solution. And then figure, well, if k is 2, then it's 2 pi plus a positive angle. That's too big. It's bigger than 2 pi. K is minus 1 or smaller, then this will be negative, right? Minus pi plus 5 pi over 12 is already negative with k equals minus 1. K equals minus 2, it's even more negative. So this is k equals 0 and k equals 1 results in the second equation. And I have exactly 4 solutions, amazingly, for x between 0 and 2 pi. So there's how you can solve those kind of problems. Trig function equals a number. Just let theta equal whatever the angle is in here, 2x in this case. Solve for theta on the unit circle, and then put back x to see which values are between 0 and 2 pi. It works really well. And you can solve all these things. Trig function equal a number. Right? All right, so let's try a little harder one. What if I did tangent, right? Let's try solving tangent 3x equals minus square root 3. And let's say for all solutions this time, I won't restrict x. At least I'll make that part easier. How do I solve tangent x equals a number? Once again, I rewrite the argument of tangent 3x equals theta to write this as tangent theta equals minus square root 3, and then I can solve it on the unit circle. How do I solve tangent theta equals minus square root 3. Again, you may have done these a little differently depending on the book you pick, but rewrite it as a ratio, minus square root 3 over 1. Right? And then to put it on the unit circle, you can divide top and bottom by the root sum square of those numbers. Minus square root 3 squared plus 1 squared is square root 4 is 2. So if I divide the top and bottom by 2, I'll get a point on the unit circle. I get minus square root 3 over 2 over a half. How about that? And so this could be y and this could be x because now this is a point on the unit circle whose ratio is tangent. Or one more choice, right? I could take minus this one over minus this one and get plus square root 3 over 2 over minus a half. And this could be y and this could be x. And they're both viable solutions, right? There's 2 points in the unit circle that have that. So suppose x is a half and y is minus square root 3 over 2. That point. And the other one for tangent, cotangent is always the opposite direction, but we can figure it out. Minus a half and plus square root 3 over 2 was the other. Those are the two terminal rays that are possible. Only those terminal rays will work to make tangent theta equal minus square root 3. When I drop a perpendicular, recognize, oh, 1/2 this way, square root 3 over 2 this way because I went down to minus square root 3 over 2, makes this a 60-degree angle, right? Pi over 3. As always, the opposite one is always the same by symmetry. That's pi over 3. Now I recognize what angles will make the tangent tangent of theta equal minus square root 3. Let's see, if this is pi over 3, then this angle in standard position, pi back up pi over 3. One pi minus a third pi is 2/3 pi, right? That's one, and then a whole rotation back up pi over 3. That one will be 2 pi, a rotation less pi over 3. Again, doing quotients, you have to put them over common denominator. 6 pi over 3 minus pi over 3. Oh, it's 5 pi over 3. There we go. Well, I have exactly 2 values of theta within one rotation that make tangent theta equal minus square root 3. And I'll say all possible theta are, well, this one, 2 pi over 3. And this one, 5 pi over 3. But coterminal angles always work, right? Those are all possible theta within one rotation. So I add k times 2 pi, k rotations, written as 2k pi. Same thing here. There's all possible theta. Make that work. Okay. Now, actually, there's an easier way to write it. Anybody see an easier way to write this? This is kind of messy. Write this all in one statement. See how to do that? How can I make that easier? And these terminal rays are directly opposite each other. Instead of writing this one plus 2 pi plus 2 pi plus 2 pi, this one plus 2 pi plus 2 pi, I could say this one plus pi plus pi plus pi plus pi and get all angles also. So easier is just take either one of these two angles, which is your favorite. Let's choose the small one. Theta could be 2 pi over 3 plus k pi encompasses both these sets of angles. So these all come together to be 2 pi over 3 plus k pi. Now I've just got one equation. That's kind of nice. So again, k is any integer. So finally, now what do I say is all possible x? X. Right? The original problem was tangent of 3x equals minus square root 3, not tangent of theta equals minus square root 3. I'll just put back that theta equals 3x, so this is 3x. Pi over 3 plus k pi, and I'll divide by 3, right? Then I get x equals, dividing this by 3, I've got 2 pi over 9 plus k pi over 3. Let's call it k times pi over 3. There's all angles x that will satisfy this equation. Every one of them. See how nice the unit circle is? It's really beautiful instrument for solving these kinds of problems. Trig function equal a number. These are a little complicated trying the homework, but they all work out, right? So that's what you do, right? Write theta for the angle, solve it in the unit circle, and then put back whatever theta is, theta equals 3x in this thing, and find the solutions. Now, if I'd restricted the angle on top of that, then I'd have to pick out just the values of k that give me solutions between 0 and 2 pi, or whatever the restriction was. Here I just said find all solutions, so these are all solutions. If I ask you for every solution, no restriction on the angle, and you have to leave this k in here, there's an infinite selection. And then you can put on the side if you want, k equals 0, 1, minus 1, 2, minus 2, etc. All integers. We got sine or cosine equal a number. We solve it on the unit circle directly and put back what x is in terms of theta. We got tangent, then we have to do a little trick there. It's a little harder. What if we have secant or cosecant? Suppose I have this one. Solve secant half x equals square root 2 for 0 less than or equal to theta less than 2 pi. So within one rotation, find all solutions using secant. What should I do for this one? Secant is actually, let's call it 1/2 alpha instead. How about that? Instead of x, I want to use x for the coordinate of the unit circle. What I can do whenever I see a secant or a cosecant is immediately write it using the reciprocal identities, right? I'll take the reciprocal of the left equals the reciprocal of the right, and the reciprocal of the left is cosine of 1/2 alpha. Reciprocal of the right is 1 over square root 2. There we go. Now I can solve it as a cosine problem. So if you see a secant or cosecant problem, just take the reciprocals, solve it as a sine or cosine problem. And the way to do this one is recognize that 1 over square root 2, if I multiply top and bottom by square root 2, is also square root 2 over 2. Well, yeah, that looks like something out of a triangle. But we make the same substitution. We let theta equal whatever angle is here, in this case 1/2 alpha, to get cosine theta equals square root 2 over 2. And now I can solve it on the unit circle. All right. Cosine theta is the x coordinate. All right. So I can plot all x coordinates equal square root 2 over 2 as a vertical line, but x equals about 0.7. Those are all coordinates in the xy plane with x equals square root 2 over 2. There's 2 of them on the unit circle. It follows that there's only 2 terminal rays, the terminal rays that go through those points. They will make cosine equal square root 2 over 2. Now, since it's a unit circle, this is 1. And so we went out to x equals square root 2 over 2. We recognize this side of the right triangle is square root 2 over 2. And then we say, wait a minute, I memorized that triangle. Square root 2 over 2, something in 1. It was square root 2 over 2 on this side, too. That was it. And this angle within pi over 4, 45 degrees. So this time we get a 45, 45, 90 triangle by symmetry. This one's the same. All right, we just did the same rotation back this way because we went the same distance over. And so we get for the solutions, all possible theta, the solutions we see right there, pi over 4, and we can go any whole rotations plus or minus from there, so 2k pi. Or we can do this one here, we could call it minus pi over 4 if you want, it doesn't matter. I like to do it forward and call it 2 pi back up pi over 4 is 7 pi over 4. This angle here, 8 pi over 4, 2 pi less pi over 4 is 7 pi over 4. And then you can add any whole rotations to that, plus or minus. Right? So there's all possible theta for this problem. Or we converted our secant equals square root 2 to cosine equals 1 over square root 2 to make it easier for ourselves. Now, as before, now you have to convert to x. So if alpha in this case, so theta is 1/2 alpha. And now this time to get all possible alpha, we have to multiply by 2. If I multiply the first one by 2, I've got alpha equals pi over 2, multiplying that by 2, plus 4k pi. Or, multiplying this one by 2, we've got alpha equals 7 pi over 2 plus 4k pi. There's all possible alpha. Is that readable? 7 pi over 2. Okay, now this time I have a restriction. So after I find all possible alpha, I should have put here alpha. I put theta for some reason. I want to restrict alpha to be between 0 and 2 pi. I'll go back and do that now by considering small values of k, which ones make it come out between 0 and 2 pi. So all alpha now between 0 and 2 pi. I'll try k equals 0 in this one, and I get pi over 2 plus 0. That works. So that's k equals 0 in the first equation. But now if I put k equals 1, it's pi over 2 plus 4 pi. Boy, that's bigger than 2 pi. It's bigger than 4 pi, right? So that's too big. K equals 1 doesn't work. I put k equals minus 1. Pi over 2 minus 4 pi is clearly negative. That won't work. Bigger and more negative values of k just make it worse. So only the k equals 0 works for this one. I get alpha equals pi over 2. Maybe I get something from the second one. So this time, if I put k equals 0, I get 7 pi over 2. Well, that's more than 2 pi, right? 4 pi over 2 would be 2 pi. So k equals 0 doesn't work. K equals 1 or higher makes it even bigger, so that won't work. I try k equals minus 1. So I subtract 4 pi, 7 pi over 2. Well, that's 7 pi over 2 minus 8 pi over 2 is negative. That's negative. That doesn't work. There are no solutions in this second set here, right? K equals 1 is bigger than 2 pi. K equals 0 is bigger than 2 pi, and k equals negative 1 is less than 0. So there's just nothing that makes that one work. K equals 1 is the only one that works here. And so we actually get only one solution, the alpha equals 0 solution from the first equation. Only a 90-degree angle satisfies this one. How about that? Secant of 1/2 alpha equals square root 2. Any questions on that one? It's kind of complicated, isn't it? Ready for more? This is what's always trouble with mathematics is I have to wake you up about an hour into the lecture. Everybody falls asleep. I like the 50-minute classes much better. It's about our attention span is 50 minutes. And the hardest, but mathematics, the hardest material is all at the end, but when you're falling asleep, right? So got to bring a joke book somewhere in the middle, wake everybody up. I didn't bring one today. Sorry about this. Anyway, so now that was step one. If you have trig function equal a number, you solve it on the unit circle like that. Put theta equal to angle, solve it in the unit circle, and then figure out which restrictions on x you need. The second kind is to solve a linear equation in a trig function. What is a linear equation? Anybody remember that? Maybe I'll wake you up with this. To solve a linear equation in a trig function. What a linear function f of x is? Linear function in x. What was that? This is the trouble when you try and bring new terms that nobody remembers using before. In algebra, it's ax plus b. It's a number times x plus a number is a linear function, right? Why? Because its graph is a line, right? Y equals mx plus b or y equals x plus b. So it's a linear function. We're going to make a linear function in a trig function. And a linear equation in a trig function equal to a number. Well, it's even equal to 0. And so a linear equation is ax plus b equals 0. That's a linear function. This is a linear equation in one variable. So a linear equation in a trig function is just a times trig function plus b equals 0. That's all I'm talking about. Very easy. A number times a trig function plus a number equals 0. Those actually come up quite a lot in practice in your science classes, engineering class, so forth. Mathematics classes, certainly, right? How do I solve that? And I bet some of you can guess this. But we're just going to do this in small steps. Now we can solve trig function equal a number. We think of reducing this one to trig function equals a number. As follows, if you're solving ax plus b equals 0, how do you solve that in algebra? Right? You subtract b, and you divide by a. You got x equals minus b over a. It works every time. You get exactly one solution, right? As long as a isn't 0, then you wouldn't have a linear equation. So it's not 0. Same thing here. Subtract b and divide by a, and you get trig function equals minus b over a is an equivalent equation. And now you realize, wait, now it's trig function equals a number. That's the one I already solved. So when you have a linear equation and trig function, a times the trig function plus b equals 0, just use algebra. Subtract b and divide by a, and then use method 1. Trig function equals a number. That's what we'll do for today then is trig function equal a number and a linear equation, a trig function that converts to that. So suppose I have this one. Suppose we said solve for x between 0 and 2 pi. Again, we'll make this restriction. Cosine. 2 cosine x plus square root 3 equals 0. Suppose you have that equation. Well, we're going to do this in little steps. This is a linear trig equation, right? A times cosine x plus b equals 0. All I have to do is subtract b. You get 2 cosine x equals minus square root 3, and divide by a equals 2, and get cosine x equals minus square root 3 over 2. I can solve that on the unit circle. This time, I don't even have theta is equal to x. All I have to do is solve for x on the unit circle, right? I'll draw my unit circle, and I'll say, which I use x, but cosine is the x coordinate, so I'll find all those points on here with x coordinate minus square root 3 over 2. And observe that there's 2 points on the unit circle with that x coordinate, right? And by drawing the terminal rays, there's only 2 terminal rays through those points. Since this goes out to square root 3 over 2, this side of the triangle being square root 3 over 2, and this being 1, makes this a 1/2 square root 3 over 2, 1 triangle automatically by the Pythagorean theorem. I observe this angle, and this one given symmetrically, both have to be pi over 6. Right? They're both 1/2 square root 3 over 2, 1 triangle. Evidently from this, x theta can be pi over 6, or it could be minus pi over 6, or you can call it rotation less pi over 6 will be 11 pi over 6, right? This angle here, 2 pi less pi over 6, and you put them over a common denominator, it's 12 pi over 6 less pi over 6. 12 minus 1 is 11 pi over 6. Right? That's the second angle. 2 within 1 rotation. I'm actually all done right here. That's it. This theta is equal to x in this case. I don't have to go and throw out anything because I solved it only within 1 rotation to start with. Okay? Well, that'll about do it, I think. That's a good stopping point. I just want to do the real simple ones. Next time, what we can do is say, well, what about a quadratic equation and a trig function? Those are fairly common also. Finish up some of these other details on this. Try this out of 7.2. I think I gave you all these. Please do all of them if you haven't already. This is on the double and half angle things. So 7.3. Make sure you can do 1 through 10. On 7.4 that we did, there's 1 through 3. Those are the sum of the product and product of sum formulas. And then 7.5, if you could just do number 1, which is these things. Try those homework problems and bring any questions you have next time. All right. I do have my office hour coming up now, and I have an announcement too. My office hour on Thursday, I'm going to have to cancel this after class. I have a conflict and another appointment I have to make. Well, I'll keep an extra office hour tomorrow afternoon. Wednesday, MCS 103, the classroom just 2 over there. I'll be in there from 4:20 to 5:40. If you want to come by then, no office hour Thursday. Yeah, you too. Thank you.